In this video, we're going to look at the method of trigonometric substitution. This method is very effective when you're dealing with integrands that involve root of a squared minus x squared, or root of a squared plus x squared, or root of x squared minus a squared. Notice the subtle differences between all of these cases. The first case has constant squared, that's a squared, minus variable squared, so a squared minus x squared. The second case has constant squared, that's a squared, plus variable squared, that's x squared. The third case has variable squared, that's x squared, minus constant squared, that's a squared. In each cases, we will apply a different trigonometric substitution. The goal is to eliminate the radical sign, the root sign, by applying the following trig substitutions. If your integrand has root of a squared minus x squared in it, you would apply x is equal to a sine theta, and we would apply the trigonometric identity cosine squared theta plus sine squared theta is equal to 1. By applying this trig identity, we can essentially get rid of the radical and solve the integral. If your integrand involves root of a squared plus x squared, you would apply the trig substitution x is equal to a tan theta and use the trig identity 1 plus tan squared theta is equal to secant squared theta. And again, using this trig identity enables us to get rid of the radical and solve the integral. If your integral involves root of x squared minus a squared, that means variable squared minus constant squared, you would apply the trig transformation x is equal to a secant theta, and you would use the trig identity 1 plus tan squared theta is equal to secant squared theta. And again, this is of course to eliminate the radicals so that we can solve the integral. Alright, let's look at an example. Here we have integral 1 over root 4 plus x squared dx. So the pattern that we have is root of a squared plus x squared. That means we're going to apply the transformation x is equal to a tan theta. Its derivative dx is a secant squared theta d theta. Now the pattern that we have is root of 2 squared plus x squared. That means x is equal to, well, that means a is equal to 2, so we have 2 tan theta. X is 2 tan theta. Derivative of x dx, that will be 2 secant squared theta d theta. So let's simplify the integrand. In the denominator, we have root of 4 plus x squared. So let's substitute for x, let's put in 2 tan theta. We get 4 plus 2 tan theta all squared. And we get root of 4 plus 4 tan squared theta. Let's factor out the 4 from the radical, from inside the radical, and we'll get 2 root of 1 plus tan squared theta. We're now going to use a trig identity 1 plus tan squared theta is secant squared theta. So we get 2 root of secant squared theta. Now here's where it gets a little bit tricky. The root of secant squared theta is actually absolute value of secant theta. 2 times absolute value of secant theta. And we're going to get rid of the absolute value. We'll just write as 2 times secant theta. And the reason for this is because secant theta is equal to 1 over cos theta, and secant theta is positive because cosine theta is positive when theta is between pi over 2 and negative pi over 2. And this is the restriction that we have placed on the angle. So what we have shown is the integral 1 over root of 4 plus x squared dx. We have simplified this as integral 1 over 2 sec theta times dx. Dx is this part. Dx is equal to 2 secant squared theta d theta. Now the 2 cancels with the 2, and sec theta cancels with one of these sec thetas, and we will get integral of secant theta d theta. So now let's evaluate that. we have integral 1 over root 4 plus x squared dx, and we applied a trigonometric substitution, and we turned it into a trig integral. So now we have integral of secant theta d theta. So what is the antiderivative of secant theta? We memorize that to be log of sec theta plus tan theta, absolute value, plus c. But now we need to express the answer in terms of x, because the original integral is in terms of x. So we're going to create this reference triangle to do that. Our trigonometric substitution is x is equal to 2 tan theta. That means tan theta divided by 2 both sides. Tan theta is equal to x over 2. This is opposite divided by adjacent. So now let's create a triangle, a right angle triangle. Here's theta, here's 90 degrees. Tan theta is opposite over adjacent. That means opposite will be x, adjacent is 2. To find the hypotenuse, simply apply Pythagoras and we'll get root of x squared plus 4. Alright, so now what we have is, so you can see how this triangle is very useful to get our answer back in terms of x. So let's put this in a box. This is our reference triangle. Let's label it. Reference triangle. So what we have is integral 1 over root of 4 plus x squared dx. This is equal to ln of sec theta plus tan theta plus c. But we want to get the answer back in terms of x. Well, we know tan theta is x over 2. That was our original trigonometric substitution. Now, how do we get secant theta? How do we get this part in terms of x? Secant theta will be hypotenuse over adjacent. So that's going to be root of x squared plus 4, that's the hypotenuse, divided by adjacent, that is 2. So now we can get the answer, the result in terms of x. So the answer is log of secant theta, that's root of x squared plus 4, divided by 2, plus tan theta, that's x over 2, plus c. This is the answer to the integral. All right, let's go over some strategies. So basically, we have 3 different cases that we need to look at. If your integrand involves root of a squared minus a squared, we make the transformation, the trig transformation, u is equal to a sine theta. And the way to spot this is when you have root of a squared minus u squared, you have constant squared minus variable squared. For example, root of 16 minus u squared, or root of 4 minus u squared. Take the derivative, du is equal to a cos theta d theta. Apply a trig identity. Why do we apply this trig identity? The reason for it is because it enables us to eliminate the radical and solve the integral. Now, from the transformation u is equal to a sine theta, we create a right angle triangle, a reference triangle. So sine theta will be u over a, and you would solve for the missing side by applying Pythagoras. So in this case, the missing side would be root of a squared minus u squared. And sine theta, of course, is u over a. And you can also get all the other trig angles from this as well. For example, you can solve for cosine theta to be root of a squared minus u squared over a, or tan theta to be opposite over adjacent. Tan theta would be u over root of a squared minus u squared. Now, if your integral involves root of a squared plus u squared, and the way to spot this is root of constant squared plus variable squared. So you would make the transformation u is equal to a tan theta, take its derivative, du is equal to a secant squared theta d theta. Now turn the integral into a trig integral. And we're going to apply the trig identity, 1 plus tan squared theta equals secant squared theta. And we apply this trig identity so we can turn the trig integral, we can get rid of the root sign, the radical sign, and solve the resulting integral. Now, once you have the integral solved in terms of theta, you still need to go back to the original variable x, and that's where the triangle comes in. So any trig identity that appears in your answer, well, you can go to the triangle and solve it in terms of x. For example, if tan theta appears, that's opposite over adjacent, that's just going to be u divided by a. If sine theta appears, Well, sine theta will be opposite, that's u, divided by hypotenuse, that's root of a squared plus u squared. If cosine theta appears in your result, that would be adjacent, which is a, divided by hypotenuse, root a squared plus u squared. And lastly, if we have the integral, if the integral involves root of u squared minus a squared, and this is when you have variable squared minus constant squared, you would make the transformation, trig transformation, u is equal to a secant theta. Take its derivative. Derivative of secant theta is sec theta tan theta. So du would be a sec theta tan theta d theta. Apply the trig identity, 1 plus tan squared theta is equal to secant squared theta. And of course, the reason for applying this trig identity is to eliminate the radical sign within the integral so that you can solve the resulting trig integral. Now, once you solve the integral, it's still in terms of theta. So you need to bring it back to the original variable u, and we do that by applying the reference triangle. So, for example, if your result involves cosine theta, well, cosine theta would be adjacent over hypotenuse. That would be a over u. If, for example, you have secant theta in your answer, well, secant theta is going to be hypotenuse over adjacent. That's going to be u over a. Alright, so these are some of the strategies that we'll be employing in the remaining videos to come on this topic of trig substitution. Alright, thanks. I need to make some corrections to the last video. Due to a software glitch, the top row was faded out. So if your integral contains root of a squared minus u squared, that is constant squared minus variable squared, then you will apply the trig transformation u is equal to a sine theta. Similarly, if your integral is root of a squared plus u squared, constant squared plus variable squared, you will apply u is equal to a tangent theta. And lastly, if your integral contains root of u squared minus a squared, variable squared minus constant squared, you will apply this trig transformation, u is equal to a secant theta. Alright, thank you.